Hi folks! The following video is going to talk about some rearrangement reactions. In particular, I'll be focusing on ones that involve migrations to electrophilic atoms, either an electrophilic carbon, oxygen, or nitrogen. One type of rearrangement that involves a carbon electrophile is known as the Pinacol rearrangement. The starting material for the Pinacol rearrangement is a vicinal diol, so a molecule with alcohols on neighboring carbons. And the reagent for this Pinacol rearrangement is an acid such as hydronium, or H3O+. The product of the Pinacol rearrangement is a ketone, and water is released as a byproduct. And notice, looking at the starting material compared to the product, the placement of the methyl groups has changed, going from 2 each on neighboring carbons to having 1 and 3 methyl groups attached, so a rearrangement reaction has taken place in this mechanism. The first step of the Pinacol rearrangement is going to involve a proton transfer to make one of the alcohol groups into a better leaving group. I'll use one of the alcohols as the base to deprotonate hydronium. This step forms the conjugate acid of the starting material, where one of the oxygens is now cationic. This cationic oxygen is now a good leaving group, so I can have a loss of leaving group step to generate a carbocation intermediate. This step has generated the water byproduct, and in this particular example, a tertiary carbocation has formed. And it is for this carbocation intermediate that the rearrangement step can take place. So what I'm going to do is, in this case, have a methyl shift type of carbocation rearrangement. So drawing the single curved arrow from the middle of the carbon-methyl bond to the carbocation. This step shifts the methyl to create the tert-butyl group on the right side of the molecule and places the new carbocation adjacent to the alcohol group. The driving force for this carbocation rearrangement is the fact that this new carbocation is resonance stabilized. So because the carbocation is adjacent to an oxygen lone pair, to get the other resonance contributor, I could bring down that lone pair to form a pi bond. So in the other resonance form, the oxygen has 3 bonds and is now cationic. And notice that this resonance form in particular looks very similar to the ketone product. To get to the neutral final product, I need to do a final proton transfer to deprotonate the cationic oxygen. Because I'm under acidic conditions, I'm going to use water as the base. And this proton transfer will generate the neutral final product. In this case, that rearranged ketone final product, and hydronium has been regenerated as a byproduct of this last step. So in this mechanism, the step that I would call the migration to the electrophilic carbon is that rearrangement step, shifting one of the carbon groups from an adjacent carbon to the electrophilic carbocation, and this is driven by the fact that it creates a more stable carbocation intermediate. If a carbocation is resonance stabilized, you can assume that it's even more stable than a tertiary carbocation. Another type of rearrangement that involves a migration to an electrophilic carbon is known as the Benzilic acid rearrangement. The starting material for this is a diketone, where the ketones are on adjacent carbons, and typically this is performed with aromatic groups flanking these ketones. The reagent for this reaction is a hydroxide salt. And the product of this reaction is a molecule with an adjacent alcohol and carboxylate. Notice here as well that a rearrangement reaction must have taken place because in the starting material the phenols were on adjacent carbons, and in the product the 2 phenyl groups are on the same carbon. So our mechanism is going to need to account for this rearrangement. The first step of the mechanism is going to be a nucleophilic attack. The hydroxide will serve as the nucleophile, and one of the carbonyl carbons serves as the electrophile. This step generates a tetrahedral intermediate at one of the ketone carbons. The oxygen of the ketone has been converted into an anionic oxygen, and a new carbon-OH bond has formed. From this tetrahedral intermediate, I'm going to have a rearrangement step that is simultaneously going to reform the carbon-oxygen double bond at this position. I'm going to draw this with 3 curved arrows. So taking a lone pair from the anionic oxygen down to form the pi bond, taking the phenyl group and migrating it to the neighboring carbon, that is a carbonyl, and breaking the pi bond of the neighboring carbonyl center at the same time. This step reforms the carbonyl at the position that has the new OH group attached to it. Then the carbon that was formerly the carbonyl on the left now has an anionic oxygen and both phenyl groups attached to it. Thinking about acids and bases, this molecule is not in a particularly stable form because the anionic oxygen is a strong enough base to deprotonate the carboxylic acid within the molecule. Because of this, an intramolecular proton transfer will take place, and this will generate the final product where an alcohol group is present and an anionic carboxylate group is present. The reason this final proton transfer occurred is that the negative charge of the carboxylate is delocalized through resonance with a neighboring carbonyl, making that anion particularly stable. So looking at the mechanism overall and considering the key rearrangement step, the rearrangement step is driven by the fact that reforming the carbon-oxygen pi bond is very favorable because those pi bonds are particularly strong. In this case, the electrophilic carbon was a part of a carbonyl rather than a carbocation. But the same idea of the migration of a carbon group can take place for this motif as well. I now want to talk about a couple of reactions that involve migrations to electrophilic heteroatoms, either nitrogen or oxygen, instead of carbons. One example is known as the Beckmann rearrangement. The starting material of a Beckmann rearrangement is an oxime. This is an imine where the nitrogen substituent is an OH group in particular, and this is being treated with hydronium. The product of the Beckmann rearrangement is an amide, where recall that has a carbonyl attached to a nitrogen substituent. Notice that the nitrogen-oxygen bond has broken, a new carbon-oxygen bond has formed, and one of the carbon groups has migrated from a carbon to a nitrogen. So this is a fairly elaborate rearrangement reaction. The first step of the mechanism is going to be protonation of the OH group that is attached to nitrogen. I'm going to use hydronium to protonate this oxygen to make it a better leaving group. This forms a cationic intermediate, where now that water molecule is a good leaving group. Instead of having water leave to generate a nitrogen with an incomplete octet, there will be a rearrangement reaction at the same time as the loss of the water leaving group. So this may look a little bit weird at first, but it's going to involve 3 curved arrows. I'll have one of the carbon substituents migrating up to nitrogen, a loss of the water leaving group, and take the nitrogen lone pair down to form a pi bond, all in the same step. This step generated a water molecule and what's known as a nitrillium ion. So this carbon group that migrated is now attached to nitrogen. The nitrogen formed a second pi bond, making a carbon-nitrogen triple bond present in the molecule, and the nitrogen is now positively charged. A nucleophilic attack is going to occur, where the electrophilic site is this carbon that's attached to the cationic nitrogen. So I'll bring in the water nucleophile to that electrophilic carbon and break a carbon-nitrogen pi bond in the nucleophilic attack. This forms a new carbon-oxygen bond. There's now a carbon-nitrogen double bond remaining in the molecule, and the oxygen that has added is temporarily cationic. To get to a neutral intermediate, I'm going to deprotonate the cationic oxygen. Because this is occurring under acidic conditions, water is going to serve as the base in this proton transfer step. And this proton transfer generates a neutral imidate intermediate. So notice that this is not quite the amide product we're going for. So we're going to need to perform proton transfers to cause a tautomerization to the amide final product, where the position of the hydrogen and the pi bonds has changed. In the proton transfer, I'm going to use the nitrogen, which is the most basic site of this molecule, as the base, to deprotonate another equivalent of hydronium. This generates a cationic intermediate, where the nitrogen now is positively charged. There is resonance that I can draw for this intermediate involving the adjacent oxygen's lone pair and the carbon-nitrogen pi bond. So this resonance pattern will involve bringing down an oxygen lone pair to generate a carbon-oxygen pi bond, and breaking the carbon-nitrogen pi bond and bringing those electrons to nitrogen. In the other resonance form, the position of the pi bond has moved, and because the oxygen donated a lone pair to form a pi bond, that oxygen is now cationic. So this is now looking more similar to the amide final product. To get to that neutral final product, a proton transfer needs to take place. We're still under acidic conditions, so I will use water as a weak base to deprotonate the cationic oxygen. And this final proton transfer generates the neutral amide product. So looking at the second half of the mechanism, the conversion of the imidate into the amide final product, this would be an acid-catalyzed tautomerization reaction, where recall that tautomerizations are rapid equilibria between two different forms of a molecule, where which product is favored, like the amide compared to the imidate, is dictated by how strong the bonds of the product are. So before moving on, looking at this mechanism again, I want to talk a little bit more about the rearrangement step. In this particular case, the rearrangement was taking a carbon group to a nitrogen, where the nitrogen is behaving as an electrophile and is losing the water-leaving group. This is different from the reactions I showed earlier in the video, where either a carbocation or a carbonyl carbon behaved as the electrophile. One final rearrangement I want to discuss is the Baeyer-Villiger oxidation. This involves treatment of an aldehyde or ketone with RCO3H, where RCO3H is a peroxy acid. This has a carbonyl attached to an oxygen attached to an OH group, so this has an extra oxygen compared to a carboxylic acid. And the product for this reaction is an ester, where an oxygen atom has been inserted between a carbon-carbon bond in the case of a ketone. The mechanism for this reaction is going to begin with a nucleophilic attack. The oxygen on the end of the molecule that's a part of the OH group is going to serve as the nucleophile, and the carbonyl carbon is the electrophile. After this nucleophilic attack, the carbonyl carbon is now tetrahedral, the carbonyl oxygen is anionic, and the red oxygen, part of the OH group, is now cationic. An intramolecular proton transfer is going to take place, but probably not the one you expect. Rather than making this anionic oxygen neutral, the proton transfer is going to take place to make this a better leaving group. So I'm going to use the carbonyl oxygen as a base for this intramolecular proton transfer step. This makes the red oxygen neutral and the carbonyl oxygen cationic. And from this intermediate, a loss of leaving group is going to occur at the same time as a rearrangement and pi bond reformation. So this is going to have 4 curved arrows. I'm going to take down a lone pair from the anionic oxygen to reform the pi bond. I'm going to migrate one of the carbon groups to the electrophilic oxygen, that's red. I'll have a loss of leaving group from that oxygen in a way that generates a new pi bond. And I'll bring the carbon-oxygen pi bond up to the cationic oxygen. This step causes, in this case, a methyl migration to oxygen, generating the ester product. And the loss of leaving group step generates an equivalent of a carboxylic acid as well. So in terms of the migration step, you have a carbon group migrating so that a pi bond can reform. And it is this oxygen in red that was originally a part of the OH group of the peroxy acid that's serving as the electrophile. And the loss of leaving group is occurring from this electrophilic oxygen. If you have an unsymmetrical ketone or an aldehyde, the Baeyer-Villiger oxidation reaction is regioselective. One group will preferentially migrate to give a particular ester product. As an example, let's consider this ketone containing an isopropyl group and a methyl group. Treatment with a peroxy acid generates as the major product the ester where the oxygen has been inserted in between the carbonyl and the isopropyl group rather than being inserted between the carbonyl and the methyl group. For terminology, I'll say that the group that migrates is the one that becomes attached to the inserted oxygen from the peroxy acid. And the term migratory aptitude refers to the rate at which different carbon groups or hydrogen groups migrate to that electrophilic oxygen. What's experimentally observed is that hydrogen has the fastest migration rate, followed by a tertiary carbon adjacent to the carbonyl, followed by secondary carbons or phenyl groups, which have similar migration rates. Primary carbons migrate more slowly, and slowest of all are methyl groups migrating to that electrophilic oxygen. So, for example, if you wanted to predict the product for acetophenone reacting with a peroxy acid, you would want to consider the carbon groups attached to the carbonyl, in this case a phenyl group compared to a methyl group. A phenyl group has a greater migratory aptitude compared to a methyl group, meaning the phenyl migration will take place faster and by a lower barrier than the methyl migration. And based on this, you would predict that the ester product would have the oxygen from the peroxy acid inserted in between the carbonyl and the phenyl group, meaning that the phenyl group was the one that migrated in the loss of leaving group and rearrangement step. Alright, so this video talked about different types of rearrangement reactions featuring carbon electrophiles, either a carbocation or a carbonyl, or a nitrogen electrophile, or an oxygen electrophile. In class, you'll practice drawing out these mechanisms, and we'll delve a little bit more into mechanistic experiments that have been used to support the mechanisms that I showed in this video. That's it for this video. I will see you in class.